All right, this is ESYS 56B. Tonight's discussion is a lab that pertains to a power supply. The test later on this evening will be on this drawing, and the test will include questions on the different parts of the power supply. The wall outlet, 120 volts AC, is 120 volts RMS. We happen to have, whoops, get this off the screen here. Sorry, okay. So we happen to have the hot and neutral from your power supply going into the very first part of the transformer. T1 is your transformer. Here is a transformer. We'll look at this guy in great detail in a moment. Attached to this illustration happens to be a switch, happens to be a fuse. The A side is the primary side of the transformer. The B side is the secondary side of the transformer. So what do we call the A side of the transformer? Primary, okay, primary. And the B side is called? Secondary. Now, how can we tell on a transformer itself? How can we tell on a transformer itself, if we're just handed one of these, what would be primary and what would be secondary? Okay, the industry uses many transformers from industry can be ordered in such a way that there's only one pair of wires on the primary, one pair of wires on the secondary. And again, you have a pair on one side, you have a pair on the other side. How do you know which is your input? How do you know which is output? Depends on what you've ordered and what you want it to do. The transformers that we play with are going to be either voltage step up or voltage step down. So either the voltage is going to be larger on the input side, or the voltage is going to be larger on the output side. The left side is generally going to be our input, right side is going to be our output. So it all depends on the number of turns that you have in your transformer. So if we go and have a brief discussion very quickly about your transformers, if I go to show you this illustration here, and the double lines means that this is iron core. And I go to show you some things that my VPRI is the same as V1. My VSEC, which stands for secondary, is the same as V2. Then I have something known as N1, a little colon here, N2. So V1 equals primary voltage. V2 is your secondary voltage. N1 is number of primary turns or windings, however you want to think about this. And N2 equals your number of secondary windings or turns. Depends on which textbook you're subscribing to. Then there's also I1, I2 is primary current, and I2 would be secondary current. F1 is equal to F2 is equal to frequency. They're going to be the same. That won't change. Then you have P1 equals P2, and this is ideally, meaning that the power of the primary will be equal to the power of the secondary. So these are all the different items that pertain to your transformer analysis. So there is a formula, your transformer formulas. Transformer formulas. Your V1 over V2 is equal to N1 over N2. is equal to I2 over I1. And we already stated here, F1 equals F2 equals frequency, P1 equals P2, ideally is equal to power. Okay, so your transformer formulas are really nothing more than these basic formulas that I've written here for you. Now, outline these transformer formulas right here, 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 and here. So there's your transformer formulas. Now, if I were to do a simple exercise with you and say, here's a transformer. And I will hook up a load to this transformer. And the load would be, oh, let's take a look. Use this guy. RL. And let's say that this is equal to 1 kilo ohm. And if I were to give you some other parameters, and the other parameters, let us say for a moment that I happen to have 14:3. And I happen to have V1 is equal to 80 V AC. This is a typical of a exercise you're likely to encounter in a homework or a quiz or a test. And so of this, you're going to be asked several things. You're going to be asked for turns ratio is equal to blank. Step up, down is the question mark. You have to fill that in. Then we are looking for V2, I2, I1, P1, P2. So, if we go back and take a look at what N represents number of turns. If I have an N1, what did I write down for N1 would be the number of turns where? In the primary. N2 would be the number of turns where? In secondary. And where do I find N1 in my master diagram? N1 is on the left-hand side. Remember, anything on the left-hand side of that iron core is going to be primary. Anything on the right-hand side is going to be secondary, yeah? So my N1 is written up here above the primary coil. Do I have an N1 value? Yes. My N2 is written above the left-hand coil over my secondary, and do I have a value for N2? So the way you calculate your turns ratio will be 14/3. Can you go ahead and use your calculator and spit out a decimal value for that, please? Okay. So turn on, clear. We have 14 divided by 3. And so what did you calculate there, Ivan? Okay. Montavo, what did you calculate? 4.6. So we would use 2 digits after the decimal point. So we would call this out as what? 4.67. Yes, we would call this out as 4.67. That's your turns ratio. So if your turns ratio happens to be such that the number is bigger in the primary, the number of turns is bigger in the primary than in the secondary, this tells you that you have a voltage step down transformer. The number of turns that are smaller will have the smaller voltage. Did you hear that? Where do I have the smaller number of turns? On the secondary. So that means my secondary will have the smaller voltage. So this would be a voltage step down. V step down. Right there. Now, you are asked to calculate the voltage of the secondary. Calculating the voltage of the secondary is as easy as doing this. I will go ahead and use this part of the formula. Remember, I have three ratios that are equal to each other, yeah? Do I have a voltage ratio of V1 over V2 is equal to the turns ratio of N1 over N2? And is that also in turn equal to the current ratio of I2 over I1? So I have three ratios that are equal to each other. Do I have a V1? Do I have an N1? Do I have an N2? I'm looking for a V2. So can I just use this part of the formula? Let me write this out for you. V1 over V2 equals N1 over N2. I'll get us a better pen here in a moment. So we will write out the formula that we're going to use. And then we're going to fill in the formula. So I happen to have 80 over V2 is equal to 14 over 3. Did I fill in the values correctly based on the numbers around my drawing? So far, so good? All right, so how do I find, given two ratios that are equal to each other, how do I find the unknown? The method is called what? Cross multiply. Cross multiply means I'm going to multiply that one and I'm going to multiply this one, yeah? So in the cross multiplication process, the result will be 80 times 3 is equal to 14 V2, yes? 14 times, there should be a multiplication, that's implied. Now, how do I isolate V2? How do I get V2 by itself? Can I solve part of this along the way? What is 80 times 3? 240? So 240 is equal to 14 times V2. So now how do I find V2? What do I need to do? Divide both sides by 14, yes? Right? If I divide both sides by 14, what does that leave me with on the right-hand side? On the right-hand side, I have V2. Right there. On the right-hand side, I have V2. And what am I going to have on the left-hand side? Well, I'm going to have to do some math here. So turn on the calculator. 240, divide by 14. Jess, do you have a number for me, please? Okay. Ivan.
Yeah, 17.14.
Very good. And everybody should be able to confirm 17.14. 17.14 VAC. Is everybody okay with that calculation? Did you practice it? Okay, so let's go ahead and fill that in. So we happen to have 17.14 VAC. My dyslexia just crept up on me. I inverted the numbers. I do that a lot, sorry. All right.
Well, that's what happens to these guys.
Yeah, well, don't let it happen on a test, okay? That's why you should double check your calculations and make sure you write down what the calculator shows you. The calculator clearly showed 17 before the dot 14, and I wrote down 14 right before the dot 17. Anyway, all right, how about current? How are we going to find current number 2? How's that possible? Did I calculate a voltage in the secondary? Now watch where this voltage is going to exist. Remember, the VAC, the 80 VAC was measured between this tap and this tap. So between the top of the primary to the bottom of the primary, right in here, if you will, right in here is where you're going to see the 80 volts AC. Right in here, my friends, here, between the top of the secondary to the bottom of the secondary, we're going to see the 17.14 VAC. Isn't that the voltage that's being presented to the load? At this moment, on the secondary, isn't the secondary behaving like this? Isn't the secondary behaving as if it were a little AC right here attached to a 1K ohm load right there? And this is 17.14 VAC. That's how the secondary is behaving, like I've drawn in green. Doesn't appear green on the projector, but it will appear green when you look at this again on the YouTube. So the secondary behaves like an AC source to the load. Did you hear that? The secondary behaves like what? An AC source to the load. And how big is this AC source? 17.14 volts AC, because that's the voltage of the secondary based on the turns ratio. So now you have an AC value that's being presented to a 1K ohm load. Can you calculate current, please? So we're going to go ahead and take the value that we had a moment ago and divide that by 1K ohm or 1,000. And then we're going to hit enter. And when you do, Geo, what do you got for me? Gabe? Come on, read your calculator. If you divide it by 1,000. 17.14 what? Apples, oranges? Ah, yes. Right? Isn't there an exponent -3 at the end of the line? Okay.
I was just checking off what I was getting.
You divided it simply by 1,000, so it'll be 17.14. Same numerals, except it's going to be milli, because milli means to be divided by 1,000. Milliamps RMS. Okay? Is everybody all right with that secondary current? Was that easy to calculate? How do I find my primary current? I find my primary current by cross multiplying, yeah? So I'm running out of room on this piece of paper. So I will go ahead with a new piece of paper right here. And let's do this. My I2 is going to be use V1. Actually, let's use this. N1 over N2 is equal to I2 over I1. Let's use this part of the formula as opposed to the voltage. Doesn't our transformer formulas, we could use any sets of ratios equal to each other to find current, yes? Why do I want to use my turns ratios as opposed to my newly calculated voltage ratio? Well, I was given a V1, yes? Didn't I just calculate a V2? So now I have a V1 over V2, yeah? Well, here's the reason. I don't recommend using the V2 because what happens if this value is a mistake? Yeah, so if you're going to use a V2 that possibly could be in error, this voltage V2, this 17.14 VAC, that guarantees your current calculation is going to be an error. So always use a known value. N1 over N2 is a known value because those were given, yeah? So that's why in this sheet, we're going to use N1 over N2. So we're going to have, did our turns ratio, 14 over 3 is going to be equal to the current we just calculated, 17.14 milliamps over I1. So does everybody understand the formula we're going to use and how we fill in the formula to get these numbers where they sit? Now, how do I find one unknown in a pair of ratios that are equal to each other? The method was to do what? Cross multiply again. So when we cross multiply, what it is that we're going to have will be 14 times I1 is going to be equal to 3 times my 17.14 milliamps. So 14 times I1 is going to be equal to this product. So from the calculator, turn it back on, I have the current. This should still be on your calculator. Just hit multiply. When you hit multiply, it brings down your previous calculation and times 3. And when you go to do so, what is your calculated result? Times 3, times 3. Okay, so what is your calculated result? Chase. Yes, what's your result?
Is it 51.42?
Third digit, we may be a fraction of a decimal place off. I calculate 51.43 milliamps, or 51.43, milliamps. If you have 42, it's okay, we're within 1/100th of a decimal place of each other, yeah? All right, so now you have the right-hand side calculated as a result of 3 times 17.14. And now, how do I get rid of this 14 on the left side of the equation? Divide both sides by 14, yeah? And that will leave me with an I1. So if I simply now hit divide by 14, your calculated results, Jeremy?
It should be 3.67.
3.67 what?
Milliamps.
3.67 milliamps. That's your I1. Everybody okay with that number? Let's fill that in on our table. That's 3.67. 3.67 milliamps RMS. So far, so good? Okay, 2 more calculations. We got to calculate power 1. We got to calculate power 2. Now, if you remember our friend Watt's laws, good old Watt's laws, one of the most popular versions of Watt's law that people like using, PIV, yes? So if I am looking for power of the primary, wouldn't that be, if I cover up the P, is equal to an I times a V, yes? Which I? Which I? Primary. Which V? V1, primary, yes? So power of the primary equals current primary times voltage primary. And we just calculated current primary, so that's 3.67 milliamps, yes? And what's the voltage of the primary? It was originally given as 80 VAC, yes? Okay. Let's go ahead and make that calculation. So we have the current still on our calculator from before. And now multiply that by the 80. And before I hit enter, I would hopefully see that you will have hit enter. So I'm looking for that answer from Mr. Montalvo. What do you have?
293.6 milliwatts.
293.6. Okay, because I'm using all the memory spaces, we could be a few hundredths of a decimal place off. This works out to be 88 milliwatts. So far, so good? Now, is everybody okay with calculating power of the primary? Let's now go ahead and calculate power of the secondary. P2 equals what? How do I set up the formula? What do you think? Gabriel, what do you think? If I'm looking for a P2, it would be equal to still, according to Watt's law, I times the V. Which I? I2, and times which V? V2. That makes sense for everybody? P2 is equal to I2 times V2. Do we have the numbers for I2? Well, we go back to our original sheet right here. Our I2 was given as 17.14 milliamps. So 17.14 milliamps. And our V2 we calculated was 17.14 VAC, yes? So 17.14 VAC. And let's go ahead and do that calculation. So I need the milliamps times this. So on mine, I'm going to go back upstairs, take the milliamps, recall that, multiply that, and now go back way upstairs, find the voltage, enter, and just, do you have a calculation for us?
Yeah, 293.78 million watts.
All right, so you have 293 point, how much? 78. Okay, my calculator still shows 88 milliwatts. If you're within a few hundredths of these numbers, great. My calculator is going to get this right on the money only because I'm using an 84, okay? So it does things a bit more accurately. But as long as you have 293 and some change, does it match pretty closely to your 293 and some change for P2? Does P1 come pretty close to your calculated P2?
Yes.
Okay? So we have power 1 equals power 2. So let's go ahead and summarize and see what it is that we experience in this particular transformer. In this particular transformer, we said, okay, right here, we determined that this was a voltage step down. So as voltage step down, is this also a current step up transformer? Did the current step up from the primary current of 3.67 and stepped up to 17.14 milliamps on the secondary? It did. So the voltage stepped down, clearly it did. It was 80 volts in the primary, came out to 17.14 volts in the secondary, but the current in the primary, 3.67, stepped up to 17.14 milliamps RMS. So all of this in theory so far is holding to your understanding of how these formulas are related to your transformer, yes? So far so good? Okay. Now that having been said, let me just go ahead and fill in this sheet with these numbers, 293.88 milliwatts, 293.88 milliwatts. Okay, so now that analysis is complete. Now, let me show you what happens with respect to a center tap. With respect to a center tap transformer, this is what you're going to have. Here, 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 here. Okay. And let me give you some parameters on this particular guy. Let's say that this side is equal to 21, and let's say this side is equal to 4.6. And let's say this side, your V1, is equal to 42 V RMS. And I'm looking for several things. In the initial analysis, we were looking for you to verify your turns ratio. We're looking for you to determine whether it's voltage step up or step down. So let's go ahead and start with turns ratio. Is blank, and V step up / down, question mark. We'll do that here. So how do we determine our turns ratio? Question goes to Ivan. How do I determine my turns ratio? Okay, and so my turns ratio is equal to, give me a formula for turns ratio. The turns ratio is simply N1 over N2. Yeah, that's the turns ratio. That's the formula we use for the turns ratio. And so when you go ahead and you take 21 divided by 4.6, what do you calculate the turns ratio to be, Ivan?
4.57.
4.57. So 4.57 is your turns ratio, yeah? So as you look at the turns ratio, do we have a larger number of turns in the primary or do we have a larger number of turns in the secondary? Larger in the primary, smaller in the secondary. What's that tell you about voltage step up or voltage step down? This is a V step down. If you have smaller number of turns in the secondary, it's a V step down. Oh, let me say this, by the way. If you take a look at these turns, everybody, 21 to 4.6. This is only a ratio. Please understand, you do not have only 21 windings in the primary. You do not have only 4.6 windings in the secondary. This simply says that the ratio is this relationship. You could very likely have 21,000 windings in the primary. You could very likely have 4,600 turns in the secondary because the wires are very fine, okay? So this is simply a ratio. It's not a count of the direct number of windings, all right? That being said, now let's go ahead and determine some things. Can we determine our V secondary? V secondary, V2, question mark. How do I set that up, Chase? How do I set that up? Give me a formula that sets that up for us, if you would, please. For V2, yes. How would what formula would I use to set this up? Okay, so we will go ahead, V1 over V2 is equal to N1 over N2, as you say. Everybody agree we could use that pair of ratios being equal to each other? Yeah. If you agree, then let's go ahead and fill in the numbers, yes? So Chase, V1 would be 42 over V2, good. And on the other side, N1 over N2 is filled in what numbers? 21 over 4.6. Everybody okay with that? Then the process is for us to do what? Cross multiply. There and there, cross multiply. When you cross multiply, you will end up with 42 times 4.6 is equal to 21 V2. So let's go ahead and take the 42, divide by 4.6. And what do you calculate on the left-hand side? 9.13 is on the left-hand side. 21 over the 21 times V2. Okay, everybody all right with that? No. It's multiply. 42 times 4.6. Much better. Okay, you end up with 193.2, yes, is equal to 21 V2, yes? Okay. Then how do I isolate my V2? Yeah, divide both sides by the 21. And when you go to do so, you discover that your V2 works out to be what value? 9.2 volts. Everybody okay with V2 being 9.2 volts RMS? So in the primary, we have 42 volts RMS. In the secondary, we have 9.2. Now, check this out. The whole thing about the center tap is the center tap equals a wire connected to the electrical center of the secondary. Okay, it's connected to the electrical center of the secondary. So if the entire voltage of the secondary, which is going to be measured from here, so this is my V2, all the way to here, and that's equal to 9.2 VRMS, then what do you think the voltage is going to be measured between that secondary wire and the center tap? What's going to be between here and here compared to the value between here and here? Half. Right, that's what your center tap will do. So we're going to take this, it'll be 4.6, yes? So we should have 4.6 V RMS, 4.6 V RMS. Everybody okay with how to reconcile the voltage on the secondary? Okay, and how to reconcile voltage to the center tap? So the key here was finding the secondary voltage and then finding half of that as being your center tap voltage. So far, so good? Now, here we go. These transformers that you have are ordered such that they can be used as voltage step up or voltage step down. It just depends on which side has the larger number of turns. If it turns out that I have a larger number of turns on the left-hand side, and I call this input, and I have smaller number of turns on the right-hand side, and I call this output, then this would be a voltage step what? Down. Larger number of turns here, smaller number of turns here means smaller voltage over here. Suppose I flip this guy around. Couldn't I flip this guy around? If I flip this guy around, hook this side up to 120 volts, and measure what's happening over here, I have lower windings here, larger number of windings here. So this, when I turn it around 180 degrees, couldn't the same transformer be used to be voltage step up? It easily can. All we have to do is what? Flip the guy around, okay? So they have, when we order these with the decidedly different ratio of number of turns of the primary to the secondary. We can use these either way. It could be used as voltage step up or voltage step down, depending upon which way we set up the orientation of input versus output. Input will always be on your left-hand side, output will always be on your right-hand side. Flip it around, input still on my left-hand side, output is still on my right-hand side. Now, check this out. The color coding does help us in this from this particular distributor, Jameco, and secondary wires are identified with the same color, and then the odd color on the third wire on that side is your center tap. So I happen to have two yellow wires and a black wire. So my two yellow wires are my secondary wires and my black wire is my center tap. And that's how we're going to use this transformer. We're going to designate this side as being our secondary. Do all of your transformers have a pair of yellow wires and a single black wire on one side?
No.
Okay, what are your matched colors?
2 white, 1 black.
2 white, 1 black? Fine. So you have 2 white wires and 1 black wire. You will go ahead and use that set, 2 white wires and 1 black wire, as being your secondary. So far, so good? What are your colors on the other side?
Yellow, black, and red.
Yellow, black, and red. Okay. The red and the black are typically going to be used for primary, and the odd color will be we're going to cap it. We won't be using it for this exercise, okay? So I happen to have an odd color. Mine happens to be blue. So we're just going to put electrical tape on it and just use this. So we'll save the red and the black as being primary, the white, the pair of whites and the black on the other side as being secondary, all right? So if you would please, we can do this. Take your power cord. Here's your power cord. You've already cut the power cord so that you have a black wire from the power cord, a white wire from the power cord. Get your copper strands and twist them tight so that there's no fraying, no stray wires. You twist them nice and tight together. And what we're going to do is, do you have a black on the primary and a black on your power cord? Yes? Okay, so watch this on the camera, if you would. I'll try to set this up so you can see better. We're going to take the two that are black wires. We're going to take the black that's from the power cord right here and attach it to the black from the primary. Put the two together like so, and then I'm going to twist these guys together like so, and then I'm going to take my wire nut. If you look at the wire nut, on the inside of the wire nut, do you see a coiled spring? Yes? You should have a pair of wire nuts. And so what you want to do, watch this carefully. While these guys are twisted together, held with one hand, I'm going to twist on the wire nut over the pair of wires, pushing in. Here we go. I'm going to take this and push in and twist, 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 and steady pressure pushing in while you're twisting. And steady pressure pushing in, and ultimately, can you feel that it can't be twisted anymore? You can even twist the pair of wires together, but if you gently tug on this, will this come loose? Like so. Should not come loose. Have you been able to complete that task?
Yes.
All right. So with the remaining wire, so the power cord has a white wire, yes?
Yeah.
And so the remaining wire on that side, let's go ahead and use the red wire and twist these two together, like I'm demonstrating under the camera, like so. Get your second wire nut and cap it and twist. So push and twist at the same time. And steady pressure pushing in, let the wire spring mechanism catch. And ultimately what will happen is one wire will start turning in spiral around the other. And so now if you gently tug on this, will that cap fall off? Should not. Has everybody been able to complete that task? Now with your remaining power cord wire, you can cut that short and fold it. Do not have any wire exposed. You could tape it against the body of the power cord. So my ground wire of the power cord, I've cut already and I've got it taped to I have it folded back. Fold it back and tape it to the body of your extension cord. So far, so good? Okay, then what I'm going to ask you to do is with your supplied electrical tape, we're going to make sure this doesn't come loose during the course of our work together. So what we're going to do is get some electrical tape and tape all this together. So here's some electrical tape. So I'm going to pull off maybe 4 or 5 inches of electrical tape. Snip it. Now let me give you a tip on what to do when you snip electrical tape. When you snip electrical tape off of a spool like this, it's hard to tell with my black gloves on, I apologize. But what I recommend that you do is you create a tab by folding part of the tape onto itself. My friends, watch this on the screen. Here's the piece of electrical tape after I've cut it. Just fold this over on itself to create a tab. That'll make it a lot easier for the next person to pull tape off the tab. Is that a helpful idea?
Yes.
Okay. So with the piece of electrical tape that you did pull off, let's go ahead and capture all of this to keep this from moving. So I would go ahead and start right on the body of the electrical cord and spiral up and spiral up. Watch this and spiral up. Capture the first plug, seal that in place, and let's go ahead and do another piece. So as I cut another piece, take that tape, fold it onto itself, create a handy tab with the second piece of tape. Let's go ahead. There. Spiral up, capture the second one. And fold over. This way you have some confidence. This will not come apart. I would do one more right here. Okay, after cutting the third piece again, fold over the flap as a courtesy to the next person, like so. All right, so everybody, eyeballs on the screen. Watch what I'm going to do with my third piece of tape. Eyeballs on the screen? Okay. Because right now I have things attached like so. I don't want the pull to be problematic to start disembodying my tape from my wires. I'm going to create a fold like so. I'm going to take this and just crease it like so, and I'm going to tape around here. So there. And there. Safety is the thing. So now, if I'm pulling on these guys, I'm less likely to cause any injury to the portions that I really want protected as much as possible, okay? Okay, I'm going to come around. I'm going to put pause on the recording and come around and see how each of you are doing with this exercise. All right, so now that we have this portion assembled, and I can tug on it and nothing comes apart. The other wire of the primary is taped, cut short so no wire is exposed, and then this is taped all the way to the end so that no aspect of the wire is exposed. We're going to set this down, and we're going to take these, we're going to connect it onto the breadboard. Now these are already pre-tinned. My recommendation, so you don't bust the tinning on here, is to use needle nose pliers. You were supplied needle nose pliers for the specific purpose of giving you torque and being able to put the wires down. So you grab the wire like so, and then you very gently guide it into one of the bus rails. Find one that's cooperative and gently push it down. That's one. Put the center on anything here again. Don't shove in with the wire. If you shove in with the wire, you'll break the a certain aspect of the tinning. Rather, grab the tinned end with your needle nose and gently guide it, start it into a tie point hole. There we go. And then the third one, let's go to a bus rail here. Okay. Are those now secured onto your board? And they are, so we have one secondary on a power rail strip. We have another secondary on the opposite power rail strip, and the center tap is on any tie point in between. Do not have the secondaries connected together, right? If the secondaries are connected together, we will have havoc. So what to do is get your digital multimeter out. Get your probes ready to measure AC voltage.
You never put on a list to get a multimeter.
Oh, well, let's see. Yeah, you don't have one, huh? Okay, could you go and fetch a digital multimeter, please? I will put the recording back on pause. Sorry. All right, so now we're ready for our digital multimeter. So you get out this bad boy, plug in your common, your voltage, to the voltage position, like so. Set this up for AC voltage, there. Turn the machine on. And let's go ahead and see in a moment what we're gonna have on our secondary. So, what to do? Before I have you plug things in, can you all check each other and make sure the two secondary wires are not on the same rail? Look at your classmates. Don't look at yours. Look at each other's. Make sure we're not shorting those secondary wires. Do you agree your classmate has it connected separately?
Flying colors.
Flying colors?
Oh, yeah.
Okay. Then and only then, plug in the power cord to a receptacle. Touch your transformer. Is your transformer getting hot? And now we're going to measure the wire, because a little bit of wire will be sticking up.
Remember in DC?
Yeah, AC. It better be AC.
Okay, you said DC.
I'm sorry, that's my dyslexia catching up with me. Sorry. It's recorded too. This is embarrassing. Wow. I'm on YouTube.
Somebody cut the other end of the wire.
Well, shh, we won't record that. Anyway, so if you go to measure between the two secondary wires, a little bit of metal that's sticking up, I'm measuring 18.19 volts, and then if I watch this, watch me, watch the screen. So measuring my two outside wires, my secondary wires, I get 18.19, and if I measure between that and the secondary, the center tap, is my center tap half of the secondary? Because this was 18 and change, 1819, and then,
1912.
well, you'll get a different one. I have a slightly different model transformer than yours. Mine is a 105 532. What part number is yours?
149.71.
Well, because it's a different part number, you're going to have a different voltage.
Bonus point?
Okay, no, bonus point. So here's the key, is your center tap measuring half of your primary, half of your secondary?
Yes.
Isn't that wonderful? Yay. So, and does it make any difference where you put the red probe? If you flip it around, do you see a negative voltage in any of all of this?
No.
No, not at all, because this is AC. AC is not going to demonstrate a polarity on your multimeter. AC voltage is not going to demonstrate a polarity on your multimeter. Everybody all right with that?
Yeah.
Yay. All right, so now you have proven that you have successfully wired your transformer, and now we have voltage on the breadboard that we can use. So far, so good. Hallelujah. Now, what we're going to have you do is, these wires are nice and long, is let's see what this waveform looks like on an O-scope. So did Mr. Nabil give you O-scope leads? All right, so as we get our probes out, I made a notation to the class saying that this set of leads that have a BNC is not used for the O-scope. The BNC to these mini hooks are used from your function generator to the board. So from your function generator, we would use this. The O-scope leads are different. They are set up with this type of a probe and a alligator for ground, and generally color-coded with blue, magenta, yellow, green for identification. You want to make sure that your O-scope probe is set to the 1x position. There's a slider between 1x and 10x, so slide it to 1x. Notice here also, if you go to push on the body of the probe, it will reveal a hook coming out, and that's the hook is what you're going to use for making a connection. And then you also have an alligator for ground lead. Notice this also is the ground lead can spin around the collar of your probe so that you can get this connected at the right angle without having your probe all twisted up, okay? So what we're going to do is we're going to hook this up here to one side. Now, don't pull the wire out completely, but pull enough of the wire out that you can get good metal contact. And same here on this side, hook up the alligator. And I don't recall if I showed you guys, I did show other classes this. Please be very mindful how this Velcro comes apart. It's really hard to see with black gloves, huh? Darn. Well, I'll do my best. What I want to show you is this. As the Velcro comes out, as you take it apart, notice that the long strip of the Velcro, I have to do this on a white background. It's just not going to work otherwise. Hard enough on black. Here we go. This might be a little better for all of us. All right. Notice that on the Velcro, there happens to be an opening. So when you go to tie up your cables later on, you want to tie up your cables later on, and what you're going to do with the flap of the Velcro is you're going to fish that flap of the Velcro through that opening, like so, and then cinch it up. And that's how the lab techs, Mr. Nabil and his assistants, want to have these all put back together. Is that clear? Okay, this just keeps our lab techs happy, all right? And we want to keep them happy. All right, enough said about that. Let's move this out of the way. Move the tools out of the way. Calculators, pens and everything out of the way. And turn on your O-scopes. And we will connect in just a moment. All right, move this over here, move this over here, and move this guy over here. Yay. So we can see the O-scope going through its diagnostics. And I'm going to take my O-scope probe. I'm getting a lot of glare here, so I'm going to reduce the angle this way, so it reduces the glare. Position this way. All right, it's finished with its diagnostics. Going to focus. There we are. Very nice. And push menu off to proceed. Take your oscope, plug it into input number 1, and hit auto set, and let a waveform appear. Nice, we have a waveform. Take off your cursors because they're confusing and distracting. And use your voltage control and bring that waveform. Adjust the click to the right, click to the right. Menu off. 50 volts per division. Okay, so let's go ahead and see what we have here. Probe times 10, set to 1x, and let's see if that, well, 2 volts per division is not going to work, so we better do this. Touch this, set the probe to 10x, and then set the probe to 10x. There we go. All right, so set the probe to 10x, and you want to make sure your oscope is also set to the probe set up to 10x. How many people don't recall how to do that on the oscope? If you don't recall how to do that on the oscope, you press the yellow button, because that's your channel 1 button. It'll raise up your menu. You want to touch probe, set 10x, and right over here set to 10x. And once it is set to 10x, you can take the menu off. And when you go to do so, what does your voltage scale say on the far lower left?
13.1.
No, on the scale. The scale is 20 volts per division, yes?
Yeah.
Okay, so at 20 volts per division, you have a nice little waveform on the display. So far, so good? Okay. Now, that being said, you also can set up to do this. 20 volt, well, mine's a 20 volt peak. Can you make this waveform one? Okay, make it a little taller to fill the display screen. Is your scale now a different scale? Mine is set at 10 volts per division. What's yours set at? 10 volts per division? Okay, and so at 10 volts per division, can you see what the peak to peak is on your display?
Yeah.
What is your peak to peak, please?
36.8.
36.8, Gabriel?
Huh?
What is your peak to peak display? What's it say on your oscope?
Mine says 38.0.
Okay, 38.0 is fine. Jeremy,
Mine is not showing the PPE,
yours doesn't show the value peak to peak?
showing the seven.
Yeah, just go ahead, hit menu, and it should come back up. You should be able to see it in this part of the display. Jess, what does yours show?
I'm not seeing it, but it does say that it's like 800 millivolts.
Let me come over and take a look at each of yours. I'm going to bring this right up to my screen so you can see things a little more clearly here. And I'm going to focus and leave mine set in this fashion. And let me come over and help you out. Put this on pause. All right, my friends, now that you've been able to confirm your waveforms, and your waveforms are slightly different than mine in terms of amplitude. I have a slightly different transformer. Mine's hovering above 50 volts peak to peak. Yours is about 38 volts peak to peak. That's fine. At least all of yours are consistent. What we're going to do is from the, we're going to build a half-wave rectifier. So how we're going to build a half-wave rectifier will be this. Let's go ahead, get back to our board, and while we're on our board, we're going to bring in a diode. So a 4001 diode.
This is somebody?
Does everybody have a parts kit?
Yeah.
Oh, that's weird. It's not here. Okay, all right. Okay, I'm back. Disconnect the probe carefully. Very carefully. Oh, that guy's really liking that wire. Come on loose. Come on loose. There we go. Come on loose. Nice. All right. With your needed parts, grab 4001 diode. 4001 diode looks like this. It's a black cylinder with a silver stripe on one end. The silver stripe is your cathode. And we will go ahead and place it on our board in this fashion. So let me go ahead and straighten out some of these wires. So you want to place it on the board so that the cathode is not pointing towards the transformer. Point the cathode away from the transformer. I will hook up. Actually, we'll do it this way. Since we have a nice set of jumpers, we'll go ahead and use the jumpers. This here and hook it up there. Take this. What's that?
Are you using the HV power?
Oh, sure. Yeah, this is fine. All right, and you have a resistor, so you should have a 1K ohm resistor. Pull this guy out. And so the 1K ohm resistor, we'll go ahead and bend those wires. Let's place your resistor there to the secondary. So I'm on the output there and here. All right. Can everybody see the circuit build?
Yeah.
So do you have from the secondary at the top, the secondary bus at the top, do you have a jumper wire going onto a tie point on the board? And the tie point on the board, do we have a diode? And is the diode set up with the cathode on the right-hand side, meaning it's pointing away from the secondary? Then the cathode of the diode is then attached to a resistor, and the resistor is hooked up to the lower secondary wire right there. Okay, is everything built like so? If everything is built like so, let's go ahead and now check this out. Hook up your alligator here like so. And Let's twist this around so that we can have our probe up here and hook this up to the top of the resistor. And when you go to do so, my friends, when you go to do so, guess what your waveform looks like? Your waveform, all of a sudden, should look like this, yes? Did we go from AC to DC? Did you accomplish rectification? I will come over and help everybody. Let me come over here, put this back down onto the board. And most aspects of challenge would probably be in your circuit building. So I will come over, put the recording on pause. Leave it like so. Put the recording on pause. Okay, we're going to resume recording. And so as our probe is connected to the output, what we call the output of our rectifier, it's connected between the top of the rectifier diode on this side to ground, or top of the resistor to ground. We're measuring the output, and the output appears on our display as half wave pulsating DC, meaning we have a pulse and a flat spot, pulse and a flat spot. Now this is called half wave for a reason. So what we're going to do, we're going to get another oscope probe. With your next oscope probe, plug that in, if you would, into channel 2. And when you plug it into channel 2, this is how you're going to connect it to your circuit. So let me go to U, back to my circuit. Watch carefully. Oscope probe will go to the front end of your diode, right there, and the alligator will connect to your bottom bus rail to your secondary. So your two alligators are hooked up to the same rail at the bottom of your circuit, and your oscope, second oscope probe just lifted right there. Okay, and so what we should see is make sure your oscope probe is set to the 10x position, and make sure your oscope is set up properly on second channel. So you press the channel 2 button. You want to make sure that that is also set to 10x. And coupling is fine. Hit this off, off. And so channel 1 is on 10 volts per division. Channel 2 should be on 10 volts per division. And when I go to bring up channel 2 so that it sits on the line, and if I move this one slightly above, see here. Can you see this on the display of your scopes? Everybody, eyeballs on the screen, please.
Yes.
The blue waveform is your input waveform, meaning before the diode. The yellow waveform is the output of the diode to the load. And this is called half wave for this reason. Eyeballs on the screen. It is called half wave for this reason. Eyeballs on my screen. It's half wave because we're using the positive half cycle of the blue waveform to give us a positive half cycle on the output. We're not using the negative half cycle of the input because there will be nothing that happens there. And we're using the positive half cycle again to give us positive output. We're not using the negative half cycle to give us nothing here. So this, we're only using half of the input waveform in order to get us an output. Does everybody have a better appreciation why this is called a half wave rectifier? Are you able to get this display on your screens? Sure. Let me show you the connections on the board to the diode again. This, and so I'm using the second channel on the input side of the probe, input side of the diode, right there, and I'm using the first channel on the output side of the diode, which is on this side attached to the load, okay? So with this connection, you should be able to see what's going into the diode, what's coming out of the diode. What's going into the diode is AC, what's coming out of the diode is DC. Are you okay with that? Those connections? I will come and check through our needed documentation. All right, so on your handout, you have connected the transformer to the breadboard. That's been done successfully per the illustration. My sign off has been verbal, that's fine. And then the output voltage of the transformer, you were able to verify before. You can take your screenshot or take a cell phone picture. And you were able to determine by counting the number of divisions on your scope to determine what the waveform is, or you could use your cursors, whatever is easy for you. So the input waveform's in blue. I can turn off the output waveform of the yellow just right there. Oops, too many times. It's gone. And then bring in my cursors and put it on fine. Oops. There, and this one. To there. And so on yours, you were able to determine about 38 volts peak to peak. Mine was a little higher at 52, 51, 52. So I have 25.6 peak, double that brings me close to 51 volts peak to peak. Okay, so you have an input. Let's see, AC volts is measured on your DMM. So what did you measure on your digital multimeter? That's a good thing to do. Let's go ahead, take your digital multimeter, turn it on, read AC voltage. And as we read AC voltage, further up, focus. Okay, so as we set this up to read AC voltage, we're going to place the probes and verify our input voltage here and here. Okay, my input voltage in RMS on my transformer, 18.13 VRMS. So AC voltage measured on my digital multimeter, 18.13 VRMS. And is there any DC voltage measured on the multimeter? So select this to go to DC. Oh, sorry, DC. And I go to measure the DC voltage from here to here. And I don't expect any DC. Measured 0.001 VDC. So those are my measurements off the digital multimeter, eh? What are your measurements on your digital multimeter? Could you write them down on that part of the paper? Everybody good with that? Okay. My number of divisions to the positive peak is about 2.6. And at 10 volts per division, so I have 26 volts peak, which is approximately 52 volts peak to peak. So do you have number of divisions to your positive peak times your voltage scale? And for mine, came out to 26 volts peak, or approximately 52 volts peak to peak. So far, so good there? Filled in? So why are the oscope and the digital multimeter AC values different? Question, Montalvo, bottom of page 2. Why are oscope and digital multimeter AC values different? They're both measuring AC. How are they different? Why are they different? We're on the bottom of page 2, and the question on this page, which we've been filling in steadily, right here, asks us, why are the oscope and digital multimeter AC values different? Simply because
One is RMS.
one is RMS and the other is volts peak, right? Volts peak or peak to peak. In other words, your multimeter is set up to measure AC volts in RMS format, okay? Right there to right there. There's my RMS for my board. Yours comes out to about what, 19 volts RMS?
18.8.
You had 18 point something RMS? Okay. Okay. And your oscope, on the other hand, measures waveforms, measures peaks. So that's the reason why they're different. So then, over here, we take a look at this next thing. Did we hook up a diode after the secondary, before the 1K ohm load, and were we able to demonstrate AC on one side and positive pulsating DC on the other side? Yes? Okay, and then if we take a look at the illustration that's shown on the bottom of this page, that's in fact what you had done, all right? Slightly different colors on your secondary wires. Instead of yellow, as it is on mine, they happen to be white on yours, but we have effectively the same thing. Flip the page. And output voltage of the rectifier, okay. And output voltage of the rectifier, interestingly, let's go ahead and bring that back in. And let's go ahead and bring this over this way so we can see this like so. All right. Focus on that focal plane. Take off all the menu stuff much as possible. Take off my cursors as they're not needed. And what to do is to line up your yellow and your blue flag so that they are lined up on the 0 volts line. So we go ahead and bring this waveform, the yellow waveform, so that it's centered on the DC, 0 DC volts line. And the blue waveform is also centered on the DC volts reference line. And when you go to do so, do the peaks look identical? Okay, it looks like we're not getting any loss of voltage from one to the other. In actuality, the output is a little bit less than the input because our peak is happening somewhere, in my particular case, somewhere around a 26 volt peak. The output is going to be a little bit less. If I were to magnify this part of my oscope display, magnify this so that you can see there will be a slight difference between the two. And the reason why there's a slight difference, in order for the diode to work, it takes about 0.6 volts or 0.65 volts to turn on that diode. We can't see that slight difference lost in this particular scale of the oscope display. I'm going to see if I can demonstrate that for you here. I'm going to move this guy down to here, change this to a different scale, and then move my blue waveform down here as well. Change it to the same scale, 5 volts per division. Ooh, it's so hard to see. It's really, really hard to see. Yeah, even at this magnification, it's hard to see the difference of peak. Usually, we would have a slight loss between the input AC waveform and the output rectified waveform. One would be, the halfway would just be a little bit less. Can't demonstrate it, it's all right. Now, what is going to happen next, and this is, we're going to hook up our capacitors. And our capacitors are going to be set up in parallel with our output resistor. So we're going to use different size capacitors in order to achieve an observation. The desired observation is for us to see the effect of different size capacitors on how they change the amount of ripple that is going to exist on our waveforms. So I would recommend doing this. I would recommend setting your oscope displays right now to the way that I've set this up. This will make it easier for you to see the changes of ripple. If you would please, touch your channel 1 and then move this knob. This knob is your vertical position knob, this one right here. And you want to turn it counterclockwise to bring the yellow flag of your channel 1 down to the first division line, right there. And you want to do the same with your channel 2. Bring that, use this knob, the vertical position knob of channel 2, bring it down so that the red and so the blue and the yellow flags are on top of each other, and set them to the same scale, 5 volts per division, okay? So could you do that, please, and get your waveform set up this way? The best way for you to see this also with your horizontal scale is to make sure your horizontal scale is set, in this particular case, what do I have this set to? 10 microseconds per division, okay? Mine is set to 10 milliseconds per division. So could you set your oscopes to be 10 milliseconds per division, and we achieve something that looks like this. I will come around and check your displays. Okay, so before we go to hook up our capacitors onto our boards, I want to teach you to pay utmost attention to the polarity of your electrolytics. What happens when you hook up an electrolytic capacitor backwards to a voltage source? It can explode if you hook it up backwards. If you hook it up forwards, it'll charge. So I hooked this up to 60 volts and I've charged this, even though this has a capacity of 200, we won't go anywhere near there. And this was a clean screwdriver shaft, unblemished. I'm going to put these two together and let's see what happens. And tap, 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 tap. Was that a good spark?
Yeah.
All right, that was a good spark. It is now discharged. Now you generally don't want to do that to any large capacitor because the spark is not good for this capacitor, because capacitors really ought not to be discharged that quickly. In a bench, on a workbench for technicians, if they encounter large capacitors in recycling, they have a special discharge probe. It looks like a cattle prod, and one end of it will attach to the ground. The other end, the metal probe, will come and touch this. But in between the ground wire and the probe, there is a huge resistor built into the handle, and that will help dissipate the charge safely. So in a work situation, technicians who encounter large capacitors don't know if it's charged or not. You're not going to do a tongue test like you would a 9-volt battery, right? You're not going to do that. So you're going to use a special probe that has a large what inside the handle? Resistor in the handle. Attach the ground wire to the ground terminal, attach the probe to the positive, and it will discharge safely. This was not a safe discharge. You saw the spark. Now, Has the metal been pitted? Is the metal damaged?
I see it from here.
Yeah, okay. That's how serious the spark is. If you had that touching your bare skin, you would have a pretty severe burn. So if it's a strong enough spark to damage the steel of this screwdriver, think about what it'll do to human flesh. Not a pretty sight. Okay, so please handle your electrolytic capacitors with utmost respect. On your electrolytic capacitors, can you see the 10 microfarad capacitor is one side marked negative?
Yes.
It is marked negative. Watch how we hook it up. Okay, we're going to demonstrate where to make the connection of the rectifier, of the filter capacitor. And if we look at our drawing of the big picture of the power supply, we should be able to see that the capacitor comes after the diode and is going to be in parallel with whatever source resistor we hook it up to. So let's go ahead and look at our lab sheet. Our lab sheet shows us exactly the same. Our capacitor will be connected across in parallel with the load resistor. And you want to do this. You want to make sure that the long lead is attached to the top of our circuit, the more positive side, if you will, and the black lead is on the negative side, marked as ground on the schematic. So remember, it's which wire? It's positive to be long, negative to be short, right? Just like your LEDs. So you have one long wire, you have one short wire. Here's the other identifying component. On your electrolytics, can you also see that there is, maybe not on this particular one, but on some of them, okay, here's one. On some of the electrolytics, you will see that there's a white band. The white band indicates the negative lead that's attached to that side of the electrolytic capacitor, okay? And if it's not color banded with a white band showing negative, thank you, the shorter lead is going to be the negative lead. So we're going to connect it in this fashion. Let's go ahead, clear the field of our probe. Wire this up so that it is going to be in parallel. So we'll just get a few more jumpers here. Let's not crowd our circuit design. Go ahead and hook this up here to here. Have our capacitor here to here, let's say. There's your capacitor. Positive on top, negative on the bottom. And one more jumper wire to go from here to here. Okay, so is our circuit build showing the addition of the capacitor to be in parallel with the load resistor? They are connected at the top of the resistor to the top of the capacitor, and the bottom of the resistor hooked up to ground, as is the negative side of the capacitor. So do I have a parallel connection? Have you completed this connection, students? I will put this on pause and come and assist. So can everybody see where your 0 volts line is? Your 0 volts line is where both of these flags are together, is the very first division marking on your oscope, yeah? So I'm bringing in a ruler. I shouldn't be using a transparent ruler, sorry. I will bring a nice yellow card. All right, this will work. So where your oscope flags are on this far left-hand side, we've decided our 0 line is going to be the first division, yes? And then, as that's our first division, that's where our 0 line is, you can see the size difference from the positive half cycle of the input waveform in blue, and you could see the output waveform in yellow, yes? And as the output waveform is in yellow, is it still pulsating DC?
Yeah.
Yes. Is the pulsating DC following the shape of the input waveform?
Yeah.
No. Here, watch what happens if I pull the cap. If I pull the cap, put this back on run. If I pull the cap, does the output waveform follow the input waveform on the positive half cycle? Yes? Now, the moment I put the cap back in, watch what happens. Now, the cap was put back in, it stopped so it doesn't move. So what happened as a result? What happened as a result, look at this again. I'm going to put this in the run mode, disconnect my cap. Everybody see half wave pulsating DC? Where is my zero on the yellow waveform? My zero on the yellow waveform is matched with the zero on the blue waveform. Where my paper border is set up, yes? Watch what happens to the yellow waveform when I put the cap back in. When I put the cap back in, watch this. Right to here, stop this, get a good stop point. So, here's the peak and here's the valley, yes? That's the peak and that's the valley. If I pull my cap, where's my peak? My peak is here and here's my valley. Peak and valley. So what did we describe ripple as being? I think I talked to you about this last week about ripple, yes? Volts ripple is the amount of voltage between the peak and the valley. How much ripple voltage do we have without the capacitor? The entire waveform, the entire half wave out, the whole peak value is ripple from here to here. How many divisions? 1, 2, 3, 4. About 5 divisions on mine. 1, 2, 3, 4, 5 at 5 volts. So I'm about 25 volt peak. The entire peak is ripple. The moment I put in the capacitor, like so, and stop this, now where is my peak? Where's my valley? And I count backwards, 1 division, 2 division, 3 division, 3.6 divisions. 3.6 times 5 is 1.8, 3.6, 1.8, so 3.6 times 5, 18 volts peak. That's my ripple now. It was 25 volts peak to peak, now it's 18 volts peak to peak. Has my ripple been reduced? Yes. It was the full 25 from here to here, now it's less. And what you're going to find as we put in different size capacitors, this amount of ripple will become less and less. Has the capacitor done its job? What's the job of the filter capacitor? What's it say in the big picture of the power supply? What's the job of the filter capacitor, Ivan? The job of the filter capacitor is to do what? What's its purpose? Smooth out the DC pulsations. Has these pulsations been smoothed out some?
Yes.
Yes, it has been smoothed out some. This capacitor is doing its job, except you're finding out that a 10 microfarad capacitor is not going to work as well as a 47. A 47 mic will work better, 100 will work even better, and a 470 will work really, really well. And each time we put in a different capacitor, we will see less and less peak-to-peak ripple. So here's the positive peak, there's the negative peak, so the difference between the two is ripple. So is this less ripple than the entire waveform at my 25 volt peak to peak? Yes. Now, where is my DC average on this? My DC average on this waveform is physically halfway between here and the valley, between the peak and the valley. Because if I were to draw a line, if this were a flexible string and I were to pull it taut, where would it straighten out? It wouldn't straighten out up here, it wouldn't straighten out down here, it would straighten right in the middle, eh? And so my DC is right at about 1, 2, 3, it's close to 15 volts DC is where this guy is coming out right now. So I would say that given this very first capacitor, I would say I would write down the following information for mine, and you're going to write down whatever is appropriate for yours. But on mine, it appears that without cap, my V rip peak to peak is approximately the full 25 volt peak to peak. And with a 47, excuse me, with a 10 microfarad cap, my V rip is now approximately 18 volts peak to peak. And my VDC, VDC would be 5, 10, 15, 18, so close to approximately 18 volts DC. So we want to make a notation on our papers where your peak to peak is without the cap. Once you put in a 10 microfarad cap, what your volts ripple peak to peak would be, and approximate what your DC voltage is going to be. I'm going to come around the room and help each of you make this determination on your boards. Okay, so we're going to look at a trend of what's happening with your filter caps. 10 microfarad, 47 microfarad, 100 microfarad, 470 microfarad. And we're going to look at voltage ripple peak to peak considerations, VDC measured with the DMM. This is what I was able to get off the oscope. This is what I was able to approximate. Now I'm going to measure my digital multimeter in the DC mode on my capacitor to ground or resistor to ground, same thing. And on mine, works out to be, looks like 1512. Okay. So 15.12 VDC. These two numbers don't have to be spot on. Remember that this voltage was an approximation. This is an actual measurement. What we want to see is a trend. And now let's go ahead and on the board, substitute the 10 microfarad cap with your 47 microfarad cap. So find your 47 microfarad cap. Be mindful of your polarities, because you know what can happen if these are wired backwards. How can you tell which one is negative on a capacitor that is not marked? It's really easy. If you take a look at the capacitor, and take a look at my capacitor, is one end, and these are marked actually. Yeah, because you should see a little plus sign on one part of the body of the capacitor. So that's your positive lead, and you should see a stripe. That's the negative side of the capacitor. Is everybody able to see that on your 47 microfarad caps? There's a little plus sign, there's a stripe for the negative. So I'm going to yank this capacitor here, put this one in its place, put one end in, put the other end in, and in doing so, your waveform will change dramatically from what I had stopped on the oscope a few moments earlier. So take a look at the change on mine. Look at the screen. Look at my screen for a moment, please. This is the image that was frozen by the oscope because I stopped the image, I stopped the run mode. This is what I had with the 10 microfarad cap. Going from a 10 microfarad cap, I'm going to change to the, put this back in the run mode. You're going to notice the positive peak of the ripple will stay where it is. But you'll see the negative peak will rise up. In other words, I will have less of this sawtooth, less of this, we'll have less ripple. And stop. Did you see that happen? That's what it is that you want to be able to see on yours, okay? This is exactly what you want to be able to see. And so here, you're going to approximate what that ripple is. And on my screen, this peak and this valley are exactly 1 division apart at 5 volts. So I'm going to fill in my chart as 5 volt peak to peak as my V ripple. My DC voltage, I'm going to approximate, again, half of this guy. So count 1 division, 2 division, 3 divisions, 4 divisions, about 4.5. 4.5 times 5. I'm going to count this as being approximately 22.5 volts DC. So first of all, do you all see less ripple by putting in the larger 47 microfarad cap? How many people don't see it? Raise your hands. Okay, I will come over to help. Pause. Okay, I've just substituted the 47 microfarad cap with a 100 microfarad cap. I've made sure that the second probe is not connected to the cap. The second probe is connected across the resistor. This way I can easily switch caps without having to disturb the probes. Now, eyeballs, look at my oscope. Okay, what does my oscope show me? My oscope shows me the waveform with the 47 microfarad cap. Watch what happens when I put this oscope back in the run mode, how the ripple will be less. It might even be straight line. Very possibly it'll be a straight line.
Did you change the buffer?
I changed to 100 microfarad capacitor.
Okay.
And as I change to 100 microfarad capacitor, it's not quite straight line, but it's less ripple. So my ripple right now is about 4 volts, peak to peak. My VDC, 5, 10, 15, 20, 23, yeah, approximating somewhere around 23 volt peak to peak. And I'm going to measure with my digital multimeter. My digital multimeter reads 22.97. 22.97 volts DC. I have a trend. There is a trend. And just because, so everybody pause from what you're doing, and let me just show you what happens when I put in the big cap. I'm now going to put in the, what size is it, 470 microfarad cap. This is a big boy. All I have to do, since I don't have any oscope leads hooked up to the cap, I can just simply yank this guy out and put this guy in. There and there. I now have a 470 microfarad cap inserted. I'm asking you to stop and just watch my screen because you don't have time to finish. So I've substituted a 470 microfarad cap in place of the 100 microfarad cap. I have experienced this trend so far. So far, my DC voltage has steadily increased. So far, my ripple has steadily decreased. With the 470 microfarad cap, I'm now going to look at the oscope. And as I'm looking at the oscope, The screen was frozen from the 100 microfarad cap. I'm going to put this back in my run mode. Watch this in the run and stop. As my ripple diminished dramatically.
Yes.
It's tiny. How much is my ripple? I would approximate this guy to be 1.5 volts, 1.5 volt peak to peak. Where's my DC? 5, 10, 15, 20, 24. Approximately 24 volts DC. And I'm going to measure this with my digital multimeter. And my digital multimeter .2372 23.72 volts DC. Okay, so even though you were not able to finish making these measurements, this is what you should see. You should see the VDC steadily increase. You should see the ripple steadily decrease, and that happens by virtue of you using larger and larger capacitors. So when you build your power supply, do you want to use small wimpy capacitors, or do you want to use big honking capacitors? Big honking capacitors. That's the conclusion for this particular part of the lab. Any questions, my friends? I wish we had a little more time so that you can do these last two measurements yourselves. If you did, great. But you need a summary sheet in a table that looks like what I have. If not, put one together. I will go ahead and save the recording. I will put it in, I will edit it, and then save it to YouTube for you to review at a later date.